For most of modern astronomy, suggesting that an object drifting through our solar system might be artificial was unthinkable. Scientists have always been cautious about extraordinary claims, and rightly so. The principle is simple. Extraordinary claims demand extraordinary evidence. Without it, speculation risks undermining trust in the scientific process. In practice, this meant that for years, the idea of alien probes was left to the realm of fiction. When Carl Sagan and Iosif Shklovsky speculated about interstellar probes in the 1960s, they did so in a theoretical context, not in response to an observed object. By the time astronomy had matured into an era of powerful telescopes and systematic surveys, the academic culture had grown even more conservative. Every comet and asteroid was assumed to be natural until proven otherwise. This caution was not unfounded. The history of astronomy is filled with apparent anomalies, later explained by natural causes. A century ago, astronomers speculated that canals on Mars indicated intelligent life. We now know they were optical illusions, products of limited telescopes and human imagination. Radio bursts once suspected to be alien signals turned out to be emissions from pulsars. More recently, puzzling fast radio bursts have been attributed to highly magnetized neutron stars. In each case, the lesson was the same. Nature is capable of producing signals and structures that look artificial at first glance. This reinforced the instinct to resist alien explanations until all natural ones are exhausted. By the mid-2010s, the mere suggestion of artificial origin for any astronomical phenomenon was enough to provoke sharp criticism from peers. It was against this backdrop that the first known interstellar visitor was detected. ʻOumuamua, discovered in 2017, challenged assumptions in ways that reignited the debate and exposed the tension between scientific caution and the willingness to explore extraordinary possibilities. In October 2017, astronomers at the Haleakala Observatory in Hawaii detected a faint, fast-moving object. At first, it was cataloged as a typical asteroid. But over the following days, its properties revealed something unprecedented. Its velocity was far too high for it to be bound to the sun. This was not a body born in our solar system. It was the first confirmed interstellar object, later named ʻOumuamua, meaning scout, in Hawaiian. What followed was one of the most debated episodes in modern astronomy. Oumuamua's brightness varied dramatically, suggesting an elongated shape, perhaps 10 times longer than it was wide. It had no visible cometary tail, no outgassing detected by our instruments, and yet its trajectory showed a subtle acceleration inconsistent with gravity alone. The explanations offered were diverse. Some proposed that it was a fragment of a disrupted planetesimal, others that it was a hydrogen iceberg or a piece of nitrogen ice. Each scenario, however, carried its own difficulties. Amid this uncertainty, Harvard astrophysicist Avi Loeb proposed a more radical possibility. Oumuamua might be artificial. In a 2018 paper, Loeb and colleague Shmuel Bialy suggested it could be a light sail, a thin, wide sheet of material propelled by starlight or laser beams. Such technology has been theorized for human use in interstellar travel projects, such as Breakthrough Starshot. Loeb argued that if humanity can conceive of it, perhaps another civilization already has. The idea drew immediate attention, not only within academia, but across the public sphere. For many, it was the first time a respected scientist had openly proposed that something observed in the sky might be alien technology. But in the scientific community, the reaction was swift and skeptical. The response from the scientific community to Avi Loeb's hypothesis was decisive. Within weeks, articles and conference talks pushed back against the idea that ʻOumuamua was anything more than a natural object. The term used most often was speculative. Critics argued that while the light sail hypothesis was creative, it lacked supporting evidence. Without direct observation of artificial features, the claim risked undermining the credibility of astrophysics. Why such strong resistance? It was partly cultural. Science advances by explaining anomalies, but explanations must be testable. Many astronomers argued that there were still natural mechanisms, exotic ices, unseen outgassing or fragmentation, that could account for ʻOumuamua's behavior. Others worried that endorsing artificial hypotheses too early would fuel sensationalist headlines and erode public trust when those ideas inevitably failed. Loeb, however, remained clear in his position. He never claimed with certainty that ʻOumuamua was alien. Instead, he called for open consideration of artificial origins as one possibility among many. Yet, as his ideas spread into the media, nuance was often lost. Headlines declared that a Harvard astronomer had discovered an alien probe, even though no such claim had been proven. This gap between cautious speculation and public interpretation illustrates a persistent challenge in science communication. The public craves definitive answers, while scientists deal in probabilities. When those two worlds collide, misrepresentation is almost inevitable. The controversy over ʻOumuamua hardened the divide. For many scientists, it reaffirmed the instinct to default to natural explanations. For others, it revealed the danger of ignoring questions simply because they feel uncomfortable. That tension lingered until new events and new data forced the conversation to evolve. By early 2025, the conversation around interstellar objects took an unexpected turn. A group of astrophysicists from leading research centers, including the SETI Institute, Penn State University, Oxford, the University of Rochester, and NASA's Jet Propulsion Laboratory, published a paper that openly reconsidered the possibilities once dismissed. The study, titled Technosignature Search of Interstellar Objects, did not claim that any object was artificial. Instead, it laid out a systematic framework. If humanity is going to observe these visitors, then we should be prepared to test whether they display signs of technology. This was not a fringe paper. It was peer-reviewed, data-driven, and written by scientists with established careers. The fact that such an article could appear in a respected journal marked a cultural shift. What had once been taboo, discussing alien probes in a scientific context, was now being treated as a legitimate line of inquiry. The authors pointed to the growing number of interstellar objects as the catalyst for change. In the space of just a few years, 3 had already been identified: ʻOumuamua, 2I, Borisov, and TR3 Atlas. With more powerful surveys coming online, dozens more are expected in the coming decades. At those numbers, ignoring anomalies is no longer an option. The paper also emphasized that the search for technosignatures is not about proving aliens exist. It is about treating all possible explanations seriously and designing observational methods that can distinguish between natural and artificial origins. The focus is not on speculation, but on developing scientific protocols that allow us to test hypotheses with evidence. For many in the field, This shift represented something profound, the formal recognition that the question itself is worth asking. If we accept that interstellar objects deserve close scrutiny, what exactly should scientists be looking for? The 2025 paper identified four broad categories of potential technosignatures, measurable features that might indicate an artificial rather than natural origin. The first is trajectory anomalies. A rock or comet follows predictable paths set by gravity and, in some cases, gentle outgassing of ice. But if an object shows acceleration that cannot be explained by these forces, like the slight deviation seen with ʻOumuamua, it becomes worth a second look. Physics leaves little room for ambiguity here. An unexplained push demands explanation. The second is spectral or color characteristics. By splitting light into its component wavelengths, astronomers can study an object's surface composition. A natural body might show signatures of silicates, carbon, or ices, but something engineered, say, a metallic coating or composite surface, could reflect light in ways nature does not produce. Detecting such anomalies would not be proof of artificiality, but it would raise important questions. The third is geometry and morphology. Nature produces irregular shapes, jagged asteroids, lumpy comets, fractured shards, but straight edges, smooth planes, or consistent ratios might hint at design. The elongated form of ʻOumuamua sparked interest because of how unusual it was compared to solar system objects. With higher resolution imaging in the future, geometry may provide critical clues. The fourth is emissions: radio, laser, or thermal. Advanced technologies could generate detectable signals, whether deliberately or as waste heat. While SETI has long searched for radio transmissions from distant stars, the new framework extends this search to interstellar objects within reach of our telescopes and antennas. Together, these four categories create a checklist, an observational strategy that transforms a vague question into a structured investigation. Rather than asking, "Is it alien?" scientists can now ask, "Does it meet any of these measurable criteria?" This approach is what elevates the conversation from speculation to science. It provides a path forward that is testable, falsifiable, and repeatable, the very foundations of the scientific method. The renewed scientific interest in interstellar objects did not emerge in a vacuum. A major catalyst was the detection of TR3 Atlas, the third confirmed interstellar visitor. Unlike ʻOumuamua or 2II Borisov, Atlas was identified early enough to allow extensive monitoring by observatories worldwide. From the outset, TR3 Atlas appeared more comet-like than its predecessors. Observations detected faint outgassing, and its orbit suggested a trajectory consistent with natural bodies. Yet, even with these indicators, the object carried intriguing features. One detail noted by researchers was its orbital alignment. It seemed unusually close to the plane of the solar system. While this could be coincidence, it raised the question: why would an object arriving from interstellar space happen to travel along such a familiar path? It was not evidence of technology, but it was reason enough to justify deeper study, and that was the key shift. The presence of TR3 Atlas proved that interstellar objects are not rare, once-in-a-lifetime events. They are recurring phenomena, destined to be detected more frequently as survey instruments improve. For scientists, this presented both a challenge and an opportunity. The challenge was to create systematic methods for study, protocols that could be applied consistently across every detection. The opportunity was the chance to build a data set large enough to test extraordinary hypotheses with rigor rather than speculation. TR3 Atlas became a turning point because it reminded the scientific community that these encounters are no longer hypothetical. We are living in an era where the galaxy occasionally sends objects through our neighborhood, and each one, whether a chunk of ice or something far stranger, offers us data that we cannot afford to ignore. Why did TR3 Atlas and its predecessors spark such a shift in thinking? The answer lies in scale. A decade ago, astronomers assumed that interstellar visitors would be rare, perhaps appearing once in a generation. But with improvements in sky surveys, that assumption collapsed. The turning point is the Vera C. Rubin Observatory, located in Chile. Once fully operational, its Legacy Survey of Space and Time, LSST, will scan the entire visible sky every few nights with unmatched sensitivity. Astronomers expect it to discover dozens of interstellar objects every decade. That sheer volume makes it impossible to treat each one as a curiosity. Instead, they become a class of objects, statistically common, and therefore worthy of systematic study. The prospect of repeated detections changes the risk calculus. If we observe a single anomalous body, it is easy to dismiss it as noise or coincidence. But if, out of dozens, even one or two show features inconsistent with natural origins, the implications would be enormous. In other words, frequency forces accountability. There is also a generational element. A new wave of astronomers has entered the field, less tied to the taboos of the past. For them, considering technosignatures is not reckless. It is simply another hypothesis to test. Combined with better tools, faster computing, and global networks of telescopes, the community now has the means to investigate questions that were once dismissed out of hand. In this way, TR3 Atlas was more than just another comet-like object. It became a symbol of inevitability. If the galaxy continues to send us these messengers, science must be ready to analyze them with both open minds and rigorous methods. Even as the field opens to new possibilities, a persistent tension remains. Many scientists, wary of public misunderstanding, are quick to classify new interstellar detections as comets or asteroids, even before all data are in. This instinct is not simply conservatism, it is a form of damage control. The reason is clear. When researchers speak of anomalies, the media often amplifies the most sensational interpretation. During the ʻOumuamua debate, Avi Loeb's speculation about light sails was often reported as a definitive claim of alien technology. In reality, he stressed that his proposal was one among several. Yet headlines condensed the nuance into something far more dramatic. Scientists know that once the idea of an alien spacecraft reaches the public, it takes on a life of its own. Even when later evidence favors a natural explanation, the correction rarely spreads as widely as the initial claim. For researchers, this cycle risks undermining trust in astronomy and fueling misinformation. Thus, some adopt what might be called a defensive classification strategy. Assume comet until proven otherwise. The benefit is avoiding runaway speculation. The downside is that real anomalies risk being dismissed too quickly. The 2025 technosignature framework attempts to correct this by encouraging consistent, measurable criteria rather than premature labels. This balance between caution and curiosity is delicate. On one side lies the responsibility to protect scientific credibility. On the other, the obligation to follow the data wherever it leads. As interstellar objects continue to arrive, the community will need to navigate this tension with transparency, precision, and care. The controversy surrounding ʻOumuamua highlighted how easily scientific nuance can be lost once it enters public discourse. Avi Loeb, for example, was careful in his writings to frame his ideas as speculation, plausible but unproven. He wrote clearly that ʻOumuamua could be artificial, not that it was. Yet, in media coverage, those distinctions often disappeared. Articles and headlines claimed that a Harvard professor had declared the object a spacecraft. On social platforms, the idea spread even further, stripped of caveats and presented as fact. By the time scientists corrected the record, the narrative had already taken hold. For the public, speculation and confirmation became blurred. This distortion is not unique to astronomy. It is a broader feature of how science interacts with mass communication. Fast-moving media ecosystems reward simplicity and certainty, not nuance. The result is that a cautious "what if" can quickly morph into "scientists say." The consequence is twofold. First, it fuels cycles of hype and disappointment. Excited audiences feel misled when later data show a mundane explanation. Second, it makes many scientists hesitant to even raise extraordinary hypotheses, fearing misrepresentation. For astronomy, this dynamic has been particularly challenging. The search for life beyond Earth captures imagination like few other topics. That very appeal, however, makes it vulnerable to distortion. The lesson of ʻOumuamua was not only about the difficulty of interpreting data, but also about the importance of precise communication, both within academia and with the public. As more interstellar visitors are discovered, this challenge will only grow. Managing it will require not just better telescopes, but also more disciplined ways of sharing what we find. When ʻOumuamua was first detected, it was treated as an astronomical oddity, a once-in-a-lifetime visitor whose mysteries might never be fully solved. That perception changed quickly with the discovery of 2I Borisov in 2019. Unlike ʻOumuamua, Borisov looked and behaved like a conventional comet, complete with a visible tail. But its trajectory confirmed what astronomers had only theorized. Interstellar visitors are not rare. They form a population large enough that our instruments, once sensitive enough, can detect them. Then came TR3 Atlas, reinforcing the pattern. With 3 confirmed detections in less than a decade, astronomers now view interstellar objects not as isolated accidents, but as part of the natural traffic of the galaxy. These bodies, icy fragments, rocky shards, perhaps more, cross stellar neighborhoods and occasionally drift into ours. This shift in perception is more than statistical. It compels organization. If such visitors are common, then scientific protocols must evolve. Ad hoc observations are no longer enough. Each detection needs rapid follow-up, spectroscopy to determine composition, photometry to measure shape and spin, radar imaging where possible, and even coordinated radio listening campaigns. The need for standardized methodology is now clear. Without it, opportunities will be lost. ʻOumuamua passed too quickly for detailed study, leaving us with more questions than answers. Borisov was better observed, but resources were stretched. TR3 Atlas has already shown the value of global cooperation, with observatories across multiple continents tracking it simultaneously. Going forward, international coordination will be essential. Shared databases, automated alert systems, and prioritized telescope time can ensure that every interstellar visitor is studied as comprehensively as possible. In short, the story has shifted from a strange anomaly to a recurring category of objects. And with repetition comes responsibility to develop the tools, frameworks, and communication strategies that can transform mystery into measurable science. For decades, concepts such as lurkers, hypothetical probes placed in stable orbits, or self-replicating von Neumann machines belonged firmly to science fiction. Arthur C. Clarke's novel, Rendezvous with Rama, envisioned a giant cylindrical craft drifting into the solar system, a purely imaginative tale when published in 1973. But today, these once fictional scenarios are being discussed within peer-reviewed astrophysics papers. Why? Because interstellar objects have made them testable. In the past, speculation about alien probes had no data against which to be measured. Now, with recurring detections like ʻOumuamua, Borisov, and TR3 Atlas, astronomers have physical targets. Real objects with real orbits and measurable properties provide the chance to examine whether any might show anomalies consistent with technology. This does not mean scientists expect to find spacecraft. Rather, it means that the framework of SETI, the search for extraterrestrial intelligence, has expanded. For most of its history, SETI focused on detecting radio transmissions from distant stars. The new paradigm recognizes that technosignatures could also be local, carried by interstellar objects passing through our system. The questions become practical. Could a probe hide among comets, blending into the population? Would artificial coatings or structures leave spectral fingerprints detectable by our instruments? Could waste heat from machinery reveal itself as an infrared excess? These are measurable, falsifiable questions, scientific in every sense. Even if every object studied proves natural, the process strengthens astronomy. It forces precision in our models, improves instrumentation, and ensures that anomalies are investigated thoroughly. And if, against expectation, one object were to defy natural explanation, the consequences would be profound. What was once confined to novels now stands as a legitimate, evidence-driven field of inquiry. Science fiction has not become reality, but it has become a framework for the kinds of science we can now pursue. With all the excitement, it is important to pause and ask, what do the observations actually show? For ʻOumuamua, data remain ambiguous. Its trajectory suggested a non-gravitational push, but no clear outgassing was detected. For 2I Borisov, the evidence was clearer. It behaved like a classic comet, its spectrum matching expectations of icy material from deep space. And for TR3 Atlas, observations so far point in the same direction. A comet, albeit with unusual traits. Crucially, no object has yet shown features that require an artificial explanation. There are no detected radio signals, no evidence of engineered geometry, and no surface spectra inconsistent with natural materials. The anomalies observed, elongated shape, orbital alignment, faint accelerations, remain within the range of what exotic natural processes could plausibly produce. This is why the 2025 technosignature framework emphasizes procedure over conclusion. The goal is not to declare interstellar objects alien, but to ensure that when anomalies appear, they are studied systematically and without bias. By applying consistent tests, measuring trajectories, analyzing spectra, modeling geometry, and scanning for emissions, astronomers can separate noise from signal with rigor. In this sense, the shift is not about evidence already found, but about readiness. The community acknowledges that every new interstellar object deserves careful investigation, not premature dismissal. Even if all prove natural, the process enriches our understanding of planetary formation across the galaxy. And if one defies natural explanation, we will be prepared to recognize it. For now, the evidence points to a simple conclusion. The objects we have studied behave as comets and asteroids. Yet the scientific door, once firmly closed, is now open just wide enough to let new questions in. In politics, there is a concept known as the Overton window, the range of ideas considered acceptable for public discussion. For much of modern astronomy, the notion that an interstellar object could be artificial lay firmly outside that window. To even suggest it risked ridicule. But thanks to recurring detections and persistent advocacy, that boundary has shifted. Avi Loeb's work, though controversial, played a key role in moving the window. By publishing formal papers that raised the possibility of artificial origins, he forced the academic community to respond. Even those who rejected his conclusions had to engage with the question. In time, this engagement softened the taboo. Today, leading institutions openly discuss technosignatures in relation to interstellar visitors, not as fact, but as a valid hypothesis to test. Younger scientists, in particular, have embraced this change. For them, the fear of damaging credibility is outweighed by the potential for discovery. They view the search for technosignatures as no different from the search for exoplanets or gravitational waves. A frontier once considered speculative, now made practical by new data and tools. The opening of the Overton window does not guarantee extraordinary discoveries, but it does mean that scientists can now ask questions without stigma, design experiments without hesitation, and publish results without being dismissed out of hand. That cultural shift matters. Progress in science often begins when forbidden questions become permissible. What was once science fiction has become a legitimate scientific inquiry. And with every new interstellar detection, the conversation grows harder to ignore. One of the most surprising effects of the interstellar object debate has been its impact beyond academia. Coverage of ʻOumuamua and TR3 Atlas reached major news networks, classrooms, and social media feeds worldwide. Suddenly, terms like light sail, technosignature, and interstellar probe were being discussed outside scientific circles. For educators and outreach specialists, this was an opportunity. Teachers reported that students asked more questions about astronomy. Interest in astrophysics programs rose. Even speculative headlines sparked curiosity that, in many cases, led people toward real science. The mere possibility of alien technology was enough to inspire a generation to look up at the night sky with fresh eyes. But alongside this excitement comes responsibility. Scientists must walk a careful line between encouraging curiosity and preventing misinformation. If the public is repeatedly led to expect dramatic revelations, only to learn that every object was natural, the result could be disappointment and disillusionment. Avi Loeb himself has acknowledged this tension. In interviews, he has emphasized that speculation should be clear and bounded, not presented as fact. Other scientists echo this view. Engage the public, but be precise. Science thrives when people are interested, but it falters when hype outpaces evidence. The conversation around interstellar visitors is therefore not just about telescopes and data. It is about trust. trust between scientists and the public, and trust that the process of discovery will be communicated with honesty. Maintaining that balance will determine whether the surge of curiosity becomes a lasting engagement or a short-lived fascination. As the Vera C. Rubin Observatory prepares to begin its full survey, the landscape of astronomy is about to change. Instead of one interstellar visitor per decade, scientists expect dozens. Each will arrive as a brief opportunity, a narrow window, before the object slips back into interstellar darkness. To make the most of these chances, astronomers are developing a playbook for discovery. The first step is rapid identification. As soon as an object shows an interstellar trajectory, global alerts must be sent. Next comes spectroscopic analysis, splitting its light to reveal composition. Then, photometric monitoring tracks its brightness to infer shape and rotation. Where possible, radar imaging can probe its surface directly. And alongside all this, radio telescopes can listen for signals, while infrared observatories search for unusual heat. The challenge is coordination. No single observatory can do it all. Success will require international collaboration, shared databases, and agreed-upon protocols. Already, networks are being built to ensure that when the next interstellar visitor appears, astronomers from Chile to Hawaii to Europe can respond in unison. This approach reflects a broader truth. Science advances most rapidly when it is systematic. The study of interstellar objects is shifting from reactive to proactive, from isolated events to an organized field. Within a decade, we may have a catalog of dozens of such objects, each described in detail, each adding to a statistical picture of what drifts between the stars. And among them, perhaps, one will surprise us. Not with certainty, but with anomalies that resist natural explanation. The possibility, however small, is enough to keep the search alive. So we end with a question. When the next interstellar messenger arrives, and it will, what will it reveal about the galaxy beyond?